So let's start with the classical infinite horizon optimal consumption problem for Merton. So what you're doing here is you are maximizing expected utility of consumption. Utility is a power utility. And then it's well known that what you're going to get is, because of power utility, you're going to get a value function that is also a power of wealth. And your optimal investment and consumption policies are all constant proportion of your wealth, right? And then this is, have a long list of criticism for this. So first of all, this means that people will change their consumption as their wealth get a shock, which is not true. People consume at a much smoother rate. And also just risk aversion itself, the P does not actually explain the amount people invest in markets. So that's the equity premium puzzle. Now to address this, there are several models has been introduced. One of them is habit formation. So what you need to do to address these things is to introduce some kind of intertemporal relationship between your preferences. So in this case, you have this habit process, which is a smooth version of your consumption. And your utility is not just utility of consumption, it's utility of consumption with respect to habit. There is this function F, which is increasing in C, decreasing in H, right? Now, so that's essentially what habit formation model generally does. And if you look at the literature, it's completely dominated by one utility function, which is called the additive or linear habit formation. You take a utility function and apply C minus H to it, right? And then almost all papers on habit formation essentially use this type of additive habit formation, right? Good thing about them is that you can essentially cheat. You transform your model to a different model that doesn't have habit in it. And you can apply martingale duality to that model, get very general results, right? And generally, you also end up doing this type of things. One is that you end up imposing some kind of constraint on your consumption, right? Because suppose that utilities have the utility function U has infinite marginal at 0, then your C minus H should be positive, right? So it means that your C should be always less than H, and this will introduce a minimum wealth. So you need to have at least a minimum wealth so that this constraint is always satisfied. It's just by model. If you have less wealth than that, then you will get bankrupt, right? It's also this utility function is not that realistic. Consider these two scenarios: that your habit has been spending $1 a year. Let's say I was living on a street, right? And suddenly you tell me you can spend $200 a year, right? Would I be happier in this scenario, or in this scenario that I've been spending $500,000 a year, and now I'm spending another 200, right? So the additive model says that actually you are more happy here, which is essentially a little bit weird, because so essentially habit formation, linear habit formation doesn't look at that level of habit at all, right? Which it should. And this is not a new criticism. Essentially, at the same time as this linear habit formation model start to work, there was multiplicative habit formation also start to work. Instead of C minus H, you do C divided by H, which scales well with H, with habit. But unfortunately, the trick here doesn't work, right? So you don't have convex duality. And there are some numerical results in Rogers' textbook, 2 pages, right? And apart from that, there are some new results coming up that they say, well, you cannot solve this problem with convex duality technique. So let's just change the model a little bit, see whether we can recover the duality technique. So you say that we cannot solve problem A, so let's see what problem we can solve with that technique, right? So here, what I'm trying, yes.
Excuse me. Please, can you go back to the example? Oh, that is not realistic because it seems to me that C minus H in the second case is lower than C minus H in the first case.
Yes. So essentially, you're consuming 200 times than your previous your habit. So you're supposed to be happier in this situation than when you're consuming just $200 more than you have.
Yeah.
Does it make sense?
Okay. Okay, good.
Yeah. Okay. Yeah. So anyways, like this problem for just multiplicative habit formation is largely unsolved. Now I'm going to go to another direction. So the other direction is that whenever you have a reference, we essentially this economic theory that says you're loss averse. If you have a reference, you're above the reference, you're going to have a concave utility function, you're risk averse. If you're below the reference, you should be loss averse. You have a convex utility function. Now, one can say that, well, if you're using a habit formation model where C is a consumption, alpha is some reference point, you should also have loss aversion there. Now, this type of loss aversion model has applied to terminal wealth maximization. There's a large literature on it. There's not many work on consumption, right? These are just few works on that, and none of them actually really deal with the like habit formation as an internal, like endogenous thing. So you have these papers where they do linear habit as shape, but they essentially either they change the definition of habit or just put some bounds on it so that duality will work. My co-author is actually what motivated our work. Have solved a problem where you do a linear habit formation, but habit is not the exponentially weighted. It's just the maximum like past consumption. So the definition of habit is different, but they use a JB equation. They get optimal feedback policies. And then I have a paper with Jenny and Erhan, which essentially we did a multiplicative habit formation on the plus size, but on the minus side, we are doing essentially imposing a constraint, meaning that it's extremely loss averse. So essentially, you loss averse part, the utility is minus infinity. So essentially, what I'm trying to say here is that there are these two gaps. One is that multiplicative habit formation, when you divide by H, is understudied, to say, and also the loss averse version of it is also not studied well. And then that's what we do. We essentially combine both these things. So we have a multiplicative habit formation utility that is also a shape. We're going to solve it through HJB, so meaning that we get optimal controls, feedback policies, and it works for general utility, not just the power exponential. Okay, so with this introduction, let me go to the details. The settable model is very standard and straightforward. So what I'm doing is I take a Black-Scholes market, I introduce C as the consumption rate, pi as the amount invested, right? This is your normal like wealth constraint. Admissibility is the same thing as usual. You just make sure that your wealth is stay positive. And then you define for each consumption like a stream, you define habit in the normal way. It's just the exponentially weighted average of your past consumption running. Just to remember, H is going to be your initial habit from now on. Rho is going to be how the rate of exponential weighting. So how you decay. As rho is large, then you decay very fast. So your habit would be much more about your recent consumption. If rho is small, you're essentially taking average. Your habit is not going to change much, right? Throughout. Then objective function is, as I promised, is going to be the expected value of discounted utility of multiplicative habit formation. So C divided by H. And it's also a S-shaped utility. It has a concave part on gain region, and it has a convex part in the loss region. And loss is when the ratio C divided by H is less than alpha, meaning that C is greater than alpha H, good, C is less than alpha H, bad, right? And then these functions U plus and U minus are kind of classic utilities, and they're general. up to this point that I'm adding two more assumptions. The first one is there to make sure that this S-shaped utility, let me show you so this is the S-shaped utility, right? Has a smooth concave envelope. It can be a non-smooth at 0, but its concave envelope should be smooth. It's a very typical assumption they do in S-shaped utility. I'm not inventing it. The other one is some kind of growth condition on U when it gets super large. Again, I need this for transversality technical conditions, right? So apart from those, these things are pretty state general, okay? So that's the problem. That's the problem I want to solve, and then you're going to end up with a value function that depends on your wealth and your habit, right? Typically. First thing to do is to reduce the dimension here. And the way I'm reducing the dimension does not depend on the form of U, depends on the multiplicative things that you divide C by H. And this is how it's done. So if you actually look at the relative wealth, relative investment, relative consumption, so instead of looking at them, just divide them by H, by your habit, then you can essentially get a like a SD for these relative things. So there will be a relative wealth, relative investment, relative consumption. And this, if you look at this and compare it with the usual budget constraint, you see that there's this terms XC that shows up. And this will essentially change the problem, right? Then there's this result that you can show that you can essentially define relative admissible policies, and there's a one-to-one relationship between your original market and these new ones. So essentially with this, you can essentially transform your original model, which has two state variables, to a model which has just one state variable, relative wealth, okay? So that's dimension reduction. And the second is what we call concavification principle, that what you do is that instead of solving this problem, you replace the utility function, S-shaped utility, with its concave envelope. And you prove that what you get out of here is going to be optimal there as well. So that's what you do, right? So this is essentially, you're going to end with these 3 steps, which I'm trying to finish quickly. So this is how I'm going to get my results. So I start from looking at the JV equation for the concavified version of the problem, the last problem I showed you. I'm going to solve it and get a candidate value function. And then at step 3, I'm just going to go back, check that it is optimal, is actually verified it's the optimal solution for both original and concave. Okay. So it's going to be just a few slides. So step 1, this is the JV equation for the concavified problem. If you look at it, this is just the infinitesimal operator for that XSDE, and this is the concavified utility function. So it should be very familiar for those who have seen like optimal consumption problems. Then what you do is usually you maximize with respect to pi and C to get your Hamiltonian, blah, 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 right? So now maximizing with respect to pi, you only need this like solution to be concave. Then you get your usual pi star, which is like this is something you've seen before. For maximization with respect to C, you need to know exactly what the concave envelope looks like. And thanks to that assumption that tells you that the concave envelope is smooth, you can actually write it down specifically as a linear function and then the U plus function, your concave part, right? And then this C0 is the point that you get your tangent, right? If I go a little bit some slide back, essentially, CS star is essentially the point that you get your tangent, and there's a function phi star is the derivative of the utility function here. Okay, so technically, once you choose your U minus and U plus, you already know what these constants are, which are going to show up later, right? So phi 0 and C0 are already known from now. Now, you make these ansatz that there is this unknown x0 is a threshold. I'm going to solve a free boundary problem. This would be the unknown. So if there's this threshold x0 such that the V prime satisfy these inequalities, then your optimal, the best value of CS star is given by this form. between 0 and x star, the threshold your C star going to be 0, and above the threshold is going to be like this. The only unknown here is v prime, essentially, and x, right? So now you do the usual stuff. You're going to substitute in your HJB, and you're going to reduce it into a nonlinear free boundary problem, right? If v prime is unknown, x0 is unknown. Not v prime, v is unknown, and x0 is unknown. So it's a free boundary problem. So now the question is how you solve this. Well, you apply Legendre transform. You can see that this first one, once you put v prime as your y, v double prime, one v double prime becomes v u, I don't know, u double prime. So this will become linear. This will still not be linear because you have this x times v prime. So you essentially apply the Legendre transform, you get something that almost is solvable. And then you do some other stuff. I don't want to show it. That's actually the technical part of the paper. Most of the paper is done for showing this result, right? So what you do, go back. Yeah. So what you do is that you essentially reduce everything to this system of first order. Unknowns are phi and psi, and there's a free boundary y0. So essentially, we have result to show that this ODE, like free boundary ODE, has a unique solution. The proof is constructive. It also gives you how you solve it, right? So it turns out to be just the bisection search for this free boundary y0. And at each term of bisection, you just solve this ODE, right? And then once you have done that, you can actually create your solution of this free boundary problem here, right? In terms of the solution of that system of ODEs, right? So everything is done once you solve the free boundary ODE, which means that you have essentially your candidate value function. And once you've done that, you can verify, right? And the verification, you get essentially your optimal consumption and pi in terms of the solution of that nonlinear free boundary problem. Everything is there. Right, and then, so essentially this is my verification theorem, another few pages of proof. So, okay, so I have 12 minutes, so maybe I can do some numerical result now. So let's just see how these optimal things look like. So I need to set up on a model. So I'm taking power utility, right? But the risk aversion or loss aversion coefficient can be different, so P and Q, right? These are the values I get. Alpha, your reference point is 75%. So above 75% of your habit is going to be good. Below 75 is going to be loss. And then these are the parameters for my Black-Scholes market. And these are the parameters for habit. And this is the subjective discount. So all the parameters in the model that I showed you. And this kind of result that you want to get. This value function, does it show you something? This is the optimal investment strategy. So that this threshold x0, below it, you're essentially going to invest constant proportion of your wealth, linear. And then after, it's going to be nonlinear. Now, you see this drop. It has a meaning. I will get back to it later. Right. This is your optimal consumption policy. Before x0, you consume nothing. After x0, you start consuming at least alpha, right? Which is expected from SJB utility type of thing. You want to compare it with other models. You cannot compare the relative wealths directly, but what you can do, you can divide the relative pi by x, which is relative wealth, then h cancels out, and that actually is going to be the ratio of pi star divided by w, which for Merton would be constant. So these red things are Merton policies. And now you can compare these policies with that. So what you're doing is that at the beginning, you invest a little more than Merton, and then you're going to invest less than Merton. You consume nothing, you're essentially saving up. You immediately consume a little more, and then you settle with less. All this settling with less is going to give you the, I don't know, like risk premium puzzle and consumption smoothing, all coming out of this, okay? So these are the general structure. Now I did some sensitivity analysis. I don't know, every parameter I have sensitivity analysis for it. And I have a story for it, but I don't want to go for the details. There's one that I think is interesting. So do you, if I go a slide back, there's this kappa here, right? So what happens if I increase kappa? Then I'm gonna make this loss part like really small, right? So essentially what I'm going to do, I'm going to enforce, as kappa goes to infinity, I'm going to enforce a constraint that C divided by H should be greater than alpha. And it should give you the subsistence level. You remember that I said that if you have such a constraint, it would give you a minimum wealth, right? And that's exactly what's happened here. So you see that, you remember the drop will eventually go to zero as kappa becomes large, meaning that you want your wealth to be above here. But this model has an advantage because in the limit, you can only solve the problem of people, we only solve the problem for wealth above H. This actually tells you what will happen below H, right? So, okay, so that's kind of sensitivity for that. Then there are other sensitivity with respect to parameters of market. Let me skip this. I want to compare with models. So sensitivity is one way of comparing with models. Another way is like, oh, there's other bunch of models that we know and solve. Let's get those things as a limiting case of my model, right? So for example, you want to get Merton. What you need to do is make alpha goes to zero so that your utility is just your U plus part is a concave utility. Make rho goes to zero as well so that your habit doesn't change, right? Then you see that by doing that, you're just going to get constant investment, constant consumption. And then similarly here, I want to get to my actual optimal consumption problem that I solved with Erhan and Jenny. So those are the black things here, right? And you can actually, by letting the utility function go to some limit, the parameterized by some parameter epsilon and kappa, you can actually get exactly the policies back, not just the thresholds. Okay. Let me finish with just the slide. So everything was for power, but I need to tell you that I did everything for general utility. So I need to show you some other utility, right? So I'm doing like exponential utility, which is because exponential utility, you keep it above zero. It's actually not, it doesn't scale. And I also do Sahara as well, which is like a different version of utility. So it works with them. I don't have a story, but it works with them. So let me finish. I'm on time. So we solve the optimal consumption problem under loss-averse version of the multiplicative habit formation. Both of these are something that was open. And then we did it not through convex duality that would not give you the optimal control. We did it by HAB, so we have optimal control. And then its model is flexible, captures all different type of behavior. And then for future work, I'm working finite horizon version of it and then see what you can do beyond Black-Scholes, like a factor model, for example. Thank you very much.